These are the contents of today's lecture: fully connected neural networks and then gradient computation. So this is a neural network, this box here, and it's presented with this sample x comma t. X is the input vector and t is the target vector. And the actual output of this neural network when its input is x is this vector y. And it is desired that y be as close to the target t as possible. The discrepancy between y and t is quantified in terms of the loss E. Now, it could be the sum square error, or it could be something else too. We just keep it general. We'll call it the loss. The neural network is parameterized in terms of a set of weights, which we shall denote as this block W. And when we want to make y as close as possible to t, that is when we want to minimize E, we do so by adjusting iteratively these weights of the neural network. If we were to apply the vanilla gradient descent algorithm, then each iteration of the neural network training would consist of this line here. W will be replaced with W minus eta times derivative of the loss E with respect to W. And eta here is a learning rate. Although neural networks are not trained with a single sample like this, and there are more sophisticated algorithms to train neural networks today than just vanilla gradient descent, we still need to know how to compute the derivative of the loss with respect to the weights, and that's the focus of this video. So the neural network is a layered structure, and in each layer we have several neurons. Shown here is layer L-1, L, and L plus 1. Each layer drives the next layer, and the total number of neurons in each layer is not necessarily the same. So in this layer L-1, the total number of neurons is N superscript L-1. Here in layer L, it's L superscript L, and so on. And these are the weights associated with a neuron K of layer L. And this is called the bias, which can be treated as a kind of a weight. Now, notice how I've indexed the weights. So this is neuron J of layer L-1, and this is neuron K of layer L. So this weight, which actually is associated with this neuron, is W superscript L, because this neuron is in layer L, and then Kj. So look at the direction of the arrow. Wkj means this neuron index J is feeding this neuron indexed K. It's reversed. This is the first layer, layer 1. And this is the sample input X. Layer 1 neurons receive the elements of this vector X. And the output of each such neuron, K, is simply Xk. So Yk superscript 1, because this is layer 1, Yk is the output of this neuron here. That's simply equal to the kth input xk of this vector x. There is no processing involved in these neurons, input neurons, and there are no weights associated with it either. Now this is a neuron in the output layer, uppercase L. This is the last layer. And for this last layer, the output YKL, the kth output, is treated as the output Yk of the entire neural network, and that should be as close as possible to the corresponding element in the target, T sub k. So Yk should be close to t sub k. That's how we would like to train the neural network. So this is an arbitrary neuron K in any layer L. And so this neuron receives as inputs the outputs of the neurons of the previous layer. So y1 superscript L minus 1 until yn superscript L minus 1. And these outputs are multiplied by these weights of this neuron. So the net input is Sk, the net input to this neuron is Sk, which is equal to summation Wkjyj, and to that we add this bias Bk. And that's the net input S sub k. The output of this neuron is Yk, which is equal to sigma of Sk. And this function, sigma, is called the sigmoid function. As these two expressions are important, let's remember them. So I have highlighted them here. Now, this bias BKL, which is added to the net input SK, can also be perceived as another weight WK naught, which is permanently tied to a output of one of the previous layer. So this BK can be replaced with WK naught. That's why the bias can also be treated as a weight. This sigmoid function belongs to a class of functions called activation functions, and they all can serve as the nonlinearity of the neurons in the neural network. This is what the sigmoid function looks like. Sigma s is 1 over 1 plus e to the negative s. And the good thing about the sigmoid function is its derivative with respect to s is equal to sigma s times 1 minus sigma s, output times 1 minus output. This is the shape of the sigmoid function. Other activation functions are shown here. There are many other activation functions. Another common one is the rectified linear unit or ReLU activation function, which is given by g of s is max of 0, s. And the loss function can be defined as half summation k of tk minus ykl whole squared. Now this is the sum square error loss or SSE loss, and that's popular in regression. We can have many other ways to define the loss. Now this yk superscript l is nothing but the output of the neural network, which is y. And if we were to apply the gradient descent algorithm, we would be using these expressions to update the weights and the biases. But even if we don't use this vanilla gradient descent algorithm, we use some extension of it. So we are still interested in finding out the derivatives of the loss function with respect to the weights and the biases. So this is our goal, and all these derivatives together form the gradient del W of E, where W is the set of all weights and biases of all neurons in all layers. Now, the way we'll proceed is, first we will derive expressions for the derivative for the output layer neurons, and then we will proceed to find out the expressions for the derivatives for the hidden layer neurons. Why hidden layers? L equals 2 through L minus 1, because when L equals 1, we don't have any weights and biases in the input layer. So we'll first find out the derivative with respect to this weight WKJL. This is equal to partial E over partial SKL times partial SKL over partial WKJL. What we did was we use the chain rule, and so we differentiated with respect to this first, and then we differentiate with respect to this. But SKL is the net input to the neuron K, which is equal to summation Wyj plus Bk, which is why its derivative partial Sk over partial Wkj is simply equal to Yjl minus 1. And so we can replace this partial S over partial Wkj with Yjl minus 1 here, and that gives us this expression here. Now we define the error delta K of this neuron K as the derivative of the loss with respect to the net input to that neuron. Now this is a generic definition. It applies to neurons in other layers as well. So this is the expression for the error delta, and using this definition we can replace this here with delta, whence we get partial E over partial W equals Yj times delta K. And this is an important expression, so let's write it down here and keep it in memory. And delta, by definition, is partial E over partial Sk. Again, applying the chain rule, I get two factors here. And this partial Y over partial Sk, since Y is nothing but sigma of Sk, so this factor here is nothing but sigma prime of Sk, the derivative of the sigmoidal function. Sigma prime Sk times partial E over partial Y. Now this derivative here, partial loss over partial yk, can be easily computed because yk is nothing but the kth element of the output of the entire neural network, and the loss will be directly, explicitly defined in terms of the output y. So this is readily obtained once you know the expression for the loss function. So this is an important expression, so let's highlight it here. Now, specifically for the sum square error loss, E is defined in this manner, whence the error delta K will be sigma prime Sk times YKL minus Tk. This is specific for the SSE loss. So we have an expression for the derivative of the loss with respect to any weight Wkj of the output layer. Now, I told you that the bias can be treated as another weight, but permanently tied to an output of 1. So if you look at this expression, we let this be equal to 1, the output be equal to 1, and we get the corresponding derivative of the loss with respect to the bias. All we did is make Yj equal to 1, and so we are left with delta K. And let's highlight it. So this is what we have seen so far. These are the expressions that we have highlighted. This is specifically for the SSE loss, and for the more general case, this is the expression for the delta of any neuron, and the derivative of the loss with respect to the weights and biases are defined in terms of the deltas. This is the definition of the delta. Now, I'll use the same definition for the neurons in the other layers too. Keep this in mind. Hidden layers. Next, we shall find the expression for the derivative of the loss function with respect to an arbitrary weight wkj of neuron k of any layer L. By the chain rule, the derivative with respect to wkj is equal to a derivative of the net input sk with respect to wkj times the derivative of the loss with respect to the net input sk. Now, sk by definition is equal to summation wkj yj plus bk. This is sk, the net input, which is summation of wkj yj plus bk. Whence its derivative with respect to wkj is simply yj, this yj here. Therefore, we can replace this partial s over partial kj with yj, giving rise to this expression here. Partial E over partial W equals yj L minus 1. It belongs to the previous layer, and this is derivative of the loss with respect to sk of this layer L. Now, delta, the error of this neuron, is by definition equal to the derivative of the loss with respect to the net input of the neuron. Whence, from this expression, if we replace partial E over partial sk with delta, we get this expression here. So now we have an expression for the derivative of the loss with respect to W in terms of Y, which can be computed, and delta. So what's remaining is to find an expression for this delta. Now, how does this sk, the net of this neuron, affect the loss E? The loss E is further downstream because this is some arbitrary layer L plus 1, which could be the output layer, and E is defined in terms of the output of the output layer. So E is further downstream. So how does E get affected by this net input sk in layer L? Now, that's indirectly. So when this sk is changed or perturbed, it affects directly the nets of the neurons of the next layer. And it is the nets of the next layer neurons then that influence E. Whence we can write delta k of this layer L neuron equals summation of the partial derivative of each SIL plus 1 over SKL times partial E over partial SIL plus 1. This is an important expression. So we have this expression. Now, by definition, delta I of this layer L plus 1 equals partial E over partial SI L plus 1. So, replacing this partial derivative with delta, we get this expression here. This is our current expression that we have. Now, observe that this summation is carried out over all neurons indexed I in layer L plus 1. The index of the summation is I. This factor here is independent of I, so we can take it outside. So this is what we have. Now, yk is sigma of sk, whence its derivative with respect to sk is sigma prime. So we can use this expression here, replacing this partial derivative with sigma prime. We get this expression for delta KL. This is our expression. here. But what remains is to simplify this factor here in this summation, but SIL plus 1 is nothing but the net input of this neuron, which is summation WIKL plus 1 YKL plus BKL. So differentiating with respect to YK, we have the partial derivative is WIK. Whence this expression here, replacing this partial derivative with W, we get this expression here. This is our final expression for delta KL. So it's an important equation. We store it aside. And let's see what we are doing here. How do we compute this delta K of layer L? In this expression here, observe that when we are trying to compute delta of this neuron K of layer L, we are actually using the deltas of the next layer L plus 1. That's why this step is called backpropagation of errors. So in the first step, what we are doing is we are assuming we have the deltas of the next layer neurons. We multiply them with these weights, and then we take the weighted sum of these deltas of the next layer neurons, and then we multiply that with sigma prime of the neuron in this layer, and that gives us this delta KL. So this is backpropagation of errors. We have to go backwards when we compute the errors. So we start from the output layer, we compute the deltas of the output layer neurons, then we step backwards one step and then backpropagate all the way to the input layer. So we have an expression for the derivative of the loss with respect to WKJ, which is Yj L minus 1 times delta KL, where delta KL is obtained through backpropagation of errors. Now, obtaining the derivative of the loss with respect to the bias instead of the weight, the bias is straightforward. All we have to do is replace this Yj with 1, and so this is our expression for the derivative of the loss with respect to the bias. And this is the last of our important expressions, so let's highlight it. So these are the summary of the steps involved in the overall algorithm. For the output layer, for any arbitrary loss, this is how we compute the deltas. This expression, this partial derivative, can be readily computed as long as the loss function is known. And then we compute, backpropagate, we compute the deltas of the hidden layer neurons, and then we increment the weights or find the derivatives later on. Now, for the input neurons, we know that Yj is simply Xj. Specifically, for the sum square error, delta is given by this expression here. So we are in a position to now write down the steps of the algorithm. So this is step 1, it's forward pass. We know that for the input neurons, the output Yi is equal to the input to the neural network itself, Xi, and then we go from layer 2 all the way to the output layer L. We compute Sk, the net input of each neuron, and then we compute the output Y as sigma of S of that neuron. And we proceed all the way to the output layer. From layer 2, we'll get the net inputs of layer 2 and the outputs of layer 2, and that will be used in computing the net inputs and outputs of layer 3 and so on. And then this is how we backpropagate. For the output layer neurons, delta KL is simply sigma prime SKL times this derivative, and this derivative can be readily computed. And then we apply backpropagation. We compute the deltas of the hidden layer neurons. We proceed backwards. And then we can compute the gradient either through a forward pass or a backpropagation. Either way is fine. All we have to do is multiply the deltas with 1 for the bias and with yj's. So we get the partial derivatives of the loss with respect to all the weights and the biases in this manner.